So in this video we'll look at some quantitative aspects of electrolysis. Quantitative meaning how much, or answering the question how much electrons or how much charge or how much current measured in amps or amperes are required to do something. A good example of this is the Hall process. They are sometimes called the Hall-Héroult process, named after inventors Charles Hall and Paul Héroult. In the traditional world, it has always historically been really difficult to obtain aluminum metal. And aluminum metal was challenging to get because it was really prominent in the world in an ore called bauxite, but it was difficult to get out of the bauxite because the melting point was above 2,000 degrees Celsius, and it was challenging to get that and took lots of energy to get there. Then along came this guy named Charles Hall, and in the late 1800s, early 1900s, he did some research and determined that we could get this bauxite to perhaps dissolve in this other liquid substance, and the other liquid substance was actually a mixture, not a mixture, but a different type of ore that heated up at a lower temperature. And so he took this substance and heated it up to about 1,000 degrees Celsius, which is called cryolite. And cryolite would dissolve the aluminum oxide or the bauxite ore into it. Then he could take and put graphite anodes inside of this melted solution, run electric current through it, and then the aluminum would actually plate out or fall to the bottom of the container. Now, this mineral, cryolite, which has sodium, aluminum, and fluorine in it, was kind of rare, but it's still used on a large scale to produce aluminum today. It takes a lot of energy to obviously heat those things up, and as a matter of fact, our book indicates that almost 2% of the electrical energy used in the United States is used to make aluminum. And since recycling aluminum requires only about 5% of that energy, it's considered a significant energy savings if we can recycle our aluminum. So with that in mind, we're going to look at some of these quantitative aspects of electrolysis and this electrocuting of different molten salts or molten substances to see if we can determine how much either charge or how much mass we can get by using a certain amount of energy. So I'm going to do two example problems, but before that, we need to look at a new conversion factor. And so far in your chemistry experience, you've probably looked at this mole wheel and known that, well, we can convert from moles to atoms, molecules, or ions, or moles to grams, or grams to moles. And then even in gases, if it's at standard temperature and pressure, we can convert between volumes of gases using 22.4. But actually, this mole wheel has one other spoke or one other method of converting, and that's what I mean by a conversion factor. And this one happens to have to do with electrons. And the electron conversion factor we're going to look at is converting between moles and an amount of charge that's possessed by the electrons. The amount of charge that's possessed by a mole of electrons is measured in something called coulombs, and there are 96,485 coulombs of charge on 1 mole of electrons. This relationship between moles of electrons and amount of charge is called the Faraday. Just like we call a mole a number of things, the Avogadro's number, this number is called the Faraday number. And it's named after Michael Faraday, who around 1800s made lots and lots of discoveries about electrolysis or energy and just numerous different scientific discoveries, one of which is the amount of charge in a mole of electrons. And so this is known as the Faraday constant, and we can use it as another step or another conversion factor to get us into electrons and charges. So here's our first sample exercise. This one comes from the textbook, and it's called Sample Exercise 20.14, if you have this particular textbook. If not, it's a good example problem of electrolysis. Calculate the grams of aluminum produced by electrolysis of molten, that means melted, aluminum chloride if 10 amperes of current are applied for 1 hour. 10 amps of current are applied for 1 hour. So there's a number of steps in this, and the first step actually has us using what the definition of the ampere is. And if you've never heard of an amp before, an ampere, that's okay. An ampere is simply equal to an amount of charge called a coulomb per second of time that those coulombs pass a particular position. So a coulomb per second is equal to an ampere. An ampere is equal to a coulomb per second. Step number one in doing this problem is to find the coulombs of charge. And since we're given amperes and an amount of time, we simply multiply those together to get the coulombs. So amperes is 10 amps, and then I converted hours to seconds right here. So this gives us 3.6 times 10 to the fourth coulombs of charge. Step number two is to use the Faraday constant, Michael Faraday constant right here, to get to moles of electrons. Since coulombs and moles of electrons are related by the Faraday constant, we can take our number of coulombs, 3.6 times 10 to the fourth coulombs, and then we can say for every 1 mole of electrons, there are 96,485 coulombs of charge. Divide those two, and we end up with 0.373 moles of electrons that are transferred to create this aluminum. Step number three then, use the chemical equation. The chemical equation in this case is, since we have molten aluminum, notice it's aluminum chloride, and so it's aluminum in its +3 state, is going to be converted to aluminum solid. And to make that conversion, or to make that happen from aluminum +3 to aluminum solid, we need to add 3 moles of electrons to make this happen. And since we have the number of moles of electrons right here, we could relate that to aluminum solid. It's a 3-to-1 ratio. And so if I write down 0.373, I have my answer first, 0.373 moles of electrons right here. For every 1 mole of aluminum, there are 3 moles of electrons that are used. Notice how our moles cancel with our moles. And then we end up with 0.124 moles of aluminum at the end. Now, it asks for the grams of aluminum, so then I have to do step 4. If it just asked for moles, I'd be done. But I have to convert from moles to grams. And if I look up aluminum on the periodic table, in 1 mole of aluminum, there's 27 grams. So 3.36 grams of aluminum would be plated out or produced from my molten AlCl3 if 10 amps of current were applied for an hour. Let's do a second example problem, and this time we're going to do these steps backwards, because in this particular problem, we're going to say we're going to ask the question, how much time is needed? In this one, we were told an amount of time. Here we're asking for the amount of time. Needed to deposit 1 gram of chromium from chromium chloride with a current of 1.5 amps or amperes. So this time the steps will be backwards of this way, where we're going to start down here and we're going to work this way back to our American Chemical Society, or amperes equals coulombs per second triangle. So step number 1 is to convert to moles. right down here, step number, just like step 4. And so we'll take our 1 gram of chromium that we want to produce, and we're going to convert that to moles. And in 1 gram of chromium, we have to divide that by 52, and that turns out to be 0.01923 moles of chromium. Okay, step number 2 is just like this one. Use the balanced equation, and we're going to take chromium and we're going to make it from chromium plus 3, because we have chromium plus 3 aqueous right here. You can see chromium's in this plus 3 charge, and to do that I need 3 electrons, and so here I need to use the equation to get the electrons, versus here I used it to get the moles of solid. Now I have the moles of solid, I want to get the electrons. So I take my 0.01923 moles of chromium. For every 3 moles of electrons, there's 1 mole of chromium. I now have my moles of electrons. Okay, once I get to that point, now I need to use the Faraday to find out how many coulombs of charge this would actually take for that number of electrons. So use the Faraday link, rewrite your number of moles of electrons, and using this conversion factor, for every 1 mole, there are 96,485 coulombs. Multiply those together and I get 5566 coulombs of charge. And now that I know my coulombs of charge, and I know my amperes that are applied, my amperes right here, my coulombs right here, I can use the American Chemical Society triangle right here to find the number of seconds, or the amount of time that will be needed to deposit. And so seconds, cover that up, is equal to coulombs per ampere. So coulombs divided by amperes, 1.5 I got from right up here, 5566 I got from right here. Divide those, and it will take about 62 minutes, which is 3,710 seconds or so. So hopefully from this several example problems, you learned 3 different things about the quantitative aspects of electrolysis. Number 1, that electrolysis simply means we're driving electrons into something to make something happen. Number 2, you learned a constant, the Faraday constant, that there are 96,485 coulombs in 1 mole. And then thirdly, you learned about the ampere, and that the ampere is a coulomb per second, or the amp as it's sometimes known, and how these quantitative aspects can allow us to do calculations with grams, moles, and molecules to find times, amount of charge, or current needed to make these happen.